Determine the range of a projectile launched over level ground as a function of the initial velocity, the launch angle, and g. So if we are launching over level ground, the initial height and the final height will be the same. They call the range capital R, so this vector delta R is going to be equal to capital R. And we're given a launch angle of theta. So the angle for the initial velocity vector is theta, and we multiply that by delta t. And then the vector going downwards here is 1/2 a times delta t squared. Because they only asked us to determine the range, we do not have to fill out the table completely for this problem. I'm going to take my initial velocity times delta t vector, and the cosine component of that is equal to r. So I have r is equal to vi delta t times cosine theta. The y component of this vector, the vi delta t times sine theta, is equal to 1/2. The acceleration, because this is a projectile, let's just say it's a ball. So if we have the force of gravity acting downwards, that's the only force acting on the object while it's in the air. So the acceleration is equal to little g. And we just want to use the length of this vector. Remember, little g is equal to 9.8. It's not negative unless you put the sign in yourself. So this length is equal to the magnitude of this vector here. So that's delta t squared. If you were to use the kinematic equations for delta r, for the x direction, delta rx is equal to r. The acceleration in the x direction is 0. v1x, that's just vi, times cosine theta, times delta t. So this is what you would get from using the position kinematic equation in the x direction. And then for the y direction, delta ry, this vector doesn't have a y component, so that would be 0. And since the acceleration is pointing down, it would be negative, but if we bring that over to the other side of the equation, if we bring this over to the other side of the equation, that would be positive, and that gives us what we have here. So the vi sine theta, that's v1y, and ay is g. So you would get this from using the position kinematic equation in component form. Okay, and we are trying to determine the range as a function of the initial velocity and the launch angle, so we can't have delta t in our answer. But we can use the equation that we have over here to solve for delta t. So I have delta t on this side, I have delta t squared on that side, so those cancel out. And then solving for delta t here gives me delta t is equal to multiply by 2, so you have 2i vi, 2 times vi times sine theta, and then divide by g. And then you can take this, and you can put it in over here, and that gives us r is equal to vi times delta t is 2vi sine theta divided by g. So this is delta t, and then I still have a cosine theta. And now everything that I have in my equation here, vi is known, theta is known, g is known. So everything I have in my equation is a known quantity. So this is the answer, but we can simplify it. And this is 2vi squared sine theta cosine theta divided by g. And you can leave the answer like this. However, if you use the trig ID, which says 2 sine theta cosine theta is equal to sine of 2 theta, which if this is a homework problem, you could just leave the answer like this. But if you use this trigonometric identity, you can write this as vi squared times sine 2 theta divided by g. You may have seen this equation in a high school physics class, and this is the range equation, this is only valid if the object lands at the same height from which it starts. Okay, so this is for launching over level ground. And what you can see if you write the equation this way is if you have the same initial velocity in all cases, what angle would you want to launch the object at so that it goes the farthest? So if you want the object to go the farthest, you want r to be as large as possible. You have sine of 2 theta. The largest value that you can have for sine is 1. If sine of 2 theta is equal to 1, sine of 90 degrees is equal to 1, so 90 is equal to 2 times theta, so this is when theta is equal to 45 degrees. So your object here will go the farthest if you launch it at 45 degrees, if you can't change the initial velocity. If you can change the initial velocity in order to get it to go farther, you would want to launch it faster. And if you look at the questions at the bottom of the page, if g is equal to 0, so if the force of gravity is equal to 0, what should r be equal to? Well, if the force of gravity is equal to 0, the object never comes back down to hit the ground, so I would say that's equal to infinity because it keeps going and never hits the ground again. And if you divide by 0 here, r goes to infinity, so yes, that agrees. If theta is equal to 90 degrees, what should r be equal to? Well, if you launch the object straight upwards, it's going to come back and hit the ground right where you launched it from. So r would be equal to 0. Does our function agree with this observation? If theta is equal to 90 degrees, 2 times theta is equal to 180 degrees, and sine of 180 is equal to 0. So yes, that agrees. Or you could even go back to what we have here. If theta is equal to 90 degrees, sine of 90 is equal to 1, but cosine of 90 is equal to 0, so something times 0 would give you 0. If VI is doubled, what happens to R? Well, we have a VI squared here, so R is proportional to VI squared. So if you double VI, since 2 squared is equal to 4, that would be R is 4 times larger than it was before, so that quadruples what you have for R.